lecture, and the floor is yours.
Yeah, thank you for the introduction. This opportunity to present our research. So just a few slides on context, on background. So I'm part of HYPER Center at Washington State University. So HYPER stands Hydrogen Properties for Energy Research. So our mission is to work with hydrogen safely, so others can do. So this lab was founded by Professor Leachman, who developed the equations of state for hydrogen that are currently implemented in RevProbe. So we're the only cryogenic hydrogen research laboratory in US academia. So we do a lot of applied development testing of liquid hydrogen storage transfer systems. We produce our own liquid hydrogen. So this is a trailer shown on the bottom here. So you can bring it anywhere if you have water and electricity. So you can start producing liquid hydrogen, use it for research purposes to fuel drones and other things. So we work with leading energy aerospace high-tech companies, including Airbus, Microsoft. Also receive government funding on fundamental and applied research. So recently we moved into a separate building, about 800-meter squared high bay facility. So we have several cryostats that where we can test liquid hydrogen systems. So we have outdoor research facility with that trailer that produces liquid hydrogen. So we can do a lot of applied research. So many companies just come to us to do quick testing, since we're quite experienced with cryogenic and low temperature hydrogen. So recently, our center was selected for awards by US Department of Energy. So one project will involve recirculating loop with multiphase hydrogen flow. So at about 20-30 Kelvin. So we will test different components, pumps, flow meters, valves, just transfer lines, since there is not enough information. Even if you can buy some components for liquid hydrogen systems, makers cannot guarantee specifications since they don't really know how these perform. So we'll be able to characterize those, recommend for industry usage, maybe develop some standards. So second project will be to build heavy-duty liquid hydrogen fuel station for trucks, cars, and eventually maybe replace all gasoline vehicles at our campus and transform them into hydrogen power vehicles. So that will be a bigger project. So this will involve maybe 2 large tanks where they will bring liquid hydrogen that we can use for both fueling and for research purposes. So we will instrument these tanks and maybe gather some data that can be used later to build the stations on broader scale. So again, yeah, these were selected for awards, but currently with new administrations, so they reconsider all awards. So there are still ongoing negotiations. So we don't know if this will be funded or not. But hopefully they will be. But today I will talk about modeling of liquid hydrogen systems, since that's my specialty in this area. So we're following different approaches when we try to model liquid hydrogen setups. So using both reduced order models, writing our own codes in MATLAB, and using computational fluid dynamics tools. So specifically, I'm using star CCM+, since it has all necessary capabilities. So today I will present several applications of both approaches to different flow regimes, different systems. So we'll start with liquid hydrogen storage. So I will illustrate how we use reduced order model. So this is a schematic of a tank. Right? So the lower part is occupied by liquid hydrogen. Then we have ullage space where gaseous hydrogen is present. So it's important to understand what will be evolution of pressure and temperature in this tank, since if you have heat leak, and you practically always will have heat leak, it will lead to evaporation of liquid hydrogen. It will build up pressure, and tanks can survive on a certain pressure level. So if pressure exceeds certain amount, they vent hydrogen outside. In most cases, they just lose this hydrogen. So we want to develop models where we can simulate tank behavior and optimize operations of those tanks. So in this case, simplest model, we consider two-node approach. So gaseous hydrogen is one node, liquid hydrogen the other node. We apply energy and mass conservation equations written here. So this energy equation written in enthalpy form, you can also write it in internal energy form. Basically, rate of change of enthalpy inside either liquid or gas can be described by this equation. There are heat leaks into that node, then energy transfer by mass flow, and moving boundary work. Then we have mass conservation equation. So rate of change in either liquid or knowledge, just balanced by mass transfer rates. Then for interface, we basically consider it as another node, but having infinitely small volume. So then energy equation becomes just this evaporation rate equation. So heat coming to that interface divided by enthalpy of vaporization will give you evaporation rate. And for other heat and mass transfer, so we're using empirical correlations. So here I will just illustrate how we validate this model. So we considered several systems. So at NASA, they published data on big tank that stored liquid hydrogen and was equipped with heat exchanger filled with helium. So they can maintain zero boil-off operation. So if cryocooler is not operating, or there is no heat extraction by helium, then pressure will build up in the system, right? As in the conventional tank. So this pressure evolution versus time, then they turn on cryocooler. So they pass cold helium through these pipes. It extracts heat from the hydrogen tank. So basically drop temperature and pressure in the tank, bring it to original state. So this is essentially a zero boil-off system with intermittent action from cryocooler. So we applied our model, calibrated it. Again, we're using some empirical constants in our mass transfer rates, but we can predict reasonably well pressure evolution in the tank and also temperature. So lower curves here correspond to liquid temperature, upper curve for temperature of the ullage in our model, and some temperature reading at some point in the ullage from experiment. So we can believe our model can at least be approximately applied to model behavior of these tanks. So then we conducted a lot of parametric studies just to understand what's the effect of tank geometry, operational condition, right? Since it's important for users, right? For example, spherical tanks will cost more and difficult to build. Vertical tank will occupy a smaller space, at least they'll have smaller footprint, but maybe not optimal, right, from heat transfer point of view, since it will have larger surface area per volume, there will be larger heat leak into that. Then we also looked at the size of the tank. So these results, two graphs here illustrate one is self-pressurization, how what time it will take to reach pressure 6 bar, starting from 3 bar at tanks with different volume in these two geometries. So sphere, so it takes longer time. So sphere is most optimal geometry for storing cryogens, since again it has lowest surface to volume ratio. This is vertical tank, and the size of the tank, you have better performance, right? And second graph shows daily boil-off. If you maintain constant pressure in the tank, so you will have to vent some of the hydrogen, since it always evaporates due to inevitable heat leaks. But you can see here that boil-off drastically drops initially when tank is relatively small. Then when you reach about maybe 100 cubic meters, so boil-off rates tend to stabilize, and most commercial tanks, they actually have right, volumes in this range. And in this case, sphere behaves closer to the vertical cylinder. That's because there is also some advantage of vertical cylinder, since there will be highest temperature will be concentrated on the top. There will be larger thermal stratification and the Ullage space, so you can vent hydrogen with highest energy, essentially, whether there will be smaller temperature distribution in this sphere. So in this case, if you vent in, then vertical cylinder behaves not as bad as a sphere. So then we did kind of studies. What would it take to or to compare different systems and figure out how much money you need to pay to store liquid hydrogen. So this hypothetical case, we have horizontal tank, assuming some cost of electricity, hydrogen, fuel cell efficiency. So we're looking at three cases. One, so we just have tank without cryocooler. Pressure reaches certain value, you need to vent hydrogen. So assuming some parameters for insulation or tank dimensions, so we'll basically lose about 0.85% per day of hydrogen to maintain pressure at the same level. So that will result in about $85 per ton day of hydrogen storage. So on the other hand, if you have cryocooler, you're using electricity, right? At this cost, you're driving cryocooler with that electricity, so it will consume certain electrical power, and that will result in only $26 per day and ton of stored hydrogen. So it's more efficient to use cryocooler, but of course there is capital cost associated with that cryocooler. You need to buy it, service it as well. So these systems are more efficient, but require, I guess, more money and maintenance. Then there is intermediate option, so you can maybe vent some of the hydrogen, but you, instead of venting directly to atmosphere, you can use it to power fuel cell that will drive cryocooler. Right? In this case, it will be intermediate system. So you will still lose some hydrogen, but smaller than in this simple venting case. And overall cost will come out to an intermediate number between these two. So you will pay $34 to store 1 ton of liquid hydrogen per day. Right? So this information is important for operators, buyers of liquid hydrogen tanks, since they generally don't have that information available, so it's difficult for them to make decisions. So with our model, we can look at different geometries, different operational conditions, so they can make create some techno-economical analysis, make most optimal decisions. So then we also work with actual liquid hydrogen producers, distributors. So they gave us information about actual operational tanks and service. This is typical example how pressure changes in liquid hydrogen tank with time. So here you can see it's several days, I think, right, about almost a week. So, and you can notice several distinct phenomena here, right? So initially they put liquid inside the tank. So they start with low pressure, tank is cold, but with time, due to heat leaks, right, pressure in the Ullage will build up. So it will reach this amount. They don't want to exceed that amount, since tank was not designed for withstand higher pressure. So they have venting system that opens when you reach that pressure, right? So pressure drops to this level, then there's again automatic system that closes venting valve. Then the system pressurizes again due to, again, heat coming from outside. Even if you have insulation, there will be heat leak, right? So then system pressurizes again, and this cycle repeats. So it's called cyclic venting in this case. Then, so the significant drops of pressure associated with liquid field. So initially they vent tank significantly to avoid pressurization due to filling event, then they add liquid, there's additional drop of pressure, and then again this longer term cycle repeats. So pressure builds up, and then when it reaches this level, it repeat cyclic venting. Then there is also, there are liquid extraction events. So those spikes you can see here is when liquid is extracted for certain use. So you need to power forklifts or other vehicles. So then there are additional pressure spikes you can notice here. They are associated with some hydrogen being returned. So when you extract liquid, usually these pipes are warm, so you need to cool them down. And then some vapor is produced in that case, and it's being returned in the tank, at least in their system. That's why you're observing those spikes. So they are, again, associated with more frequent liquid extraction by small amounts. So again, here I just show comparison between our model and experimental data. So again, we just starting with same experimental conditions. We assume this pressure limits when venting valve opens or closes, and then assuming certain frequency for liquid extraction events. So statistically, we can simulate this tank reasonably well. So we can describe pressure evolution in this sense. And second graph shows here essentially the liquid level. So it's hydrostatic pressure, pressure difference between bottom and top of the tank. So they're using inches of water coulomb to measure that in industry. So it will translate into certain fill level in the tank, right? So this and increases associated with liquid being added to the tank, and then gradually due to liquid extraction venting, so level decreases, right? Then they add another truck comes with liquid hydrogen, so they put it in, hydrostatic pressure difference between ullage and liquid increases. So this is associated with liquid level rise. So we believe our model is capable of capturing essential processes in liquid hydrogen tanks. So we can apply that specifically at request of this company to model how different changes in the system may affect boil-off losses. Again, that's ultimate metric. So you want to lose as low hydrogen as possible. So we looked at minor operational changes, what will happen if you use the existing system, but change how it operates. So for example, if you vent between two pressure levels that have smaller pressure difference between them, so when you close open valve, it will be more efficient. So you will lose less hydrogen, so daily boil-off loss. So instead of 50 kilograms per day, as it happens in the current tank, so it can be reduced maybe to 35. Then we also looked at different savings that can be achieved if you add components to the system, right? Maybe you can put cryocooler, reliquefy like gas that is returned to the tank, right? Then you can save more hydrogen, reduce daily losses. However, again, you will add capital cost to the system. It's not yet accounted, so we just looked at what will change with respect to daily loss if you modify operational condition or add additional elements. So yeah, if you're interested in this data modeling, so you can find thesis by Kyle Apple, who graduated last December from our center. So he can publish more detailed studies in this area. So now I will switch to more detailed modeling of liquid hydrogen tanks. So we used reduced order models for simplified analysis, where we have a lot of calibrations done prior to doing parametric studies. So if you use computational fluid dynamics, then presumably you can get more accurate results. So again, you still need to do validation, compare your results with experimental data. So here we're showing more or less economical approach when we use reduced order model for the liquid and CFD for the ullage. So it's more important to model processes in the gaseous part of the tank that we call ullage, since that's where significant temperature gradient will be established. And when you vent hydrogen, so you need to know at which temperature you're venting. So this is experimental tank at NASA for which data were available. And I'll show how our model, again, calibrated model compares with test data. So we can predict self-pressurization reasonably well. In this case, within few percent, at least for several hours. So again, we gain confidence that this approach is working well. And again, as I said, most advantage of CFD here is to be able to predict temperature distribution that is shown in this graph. You can see how temperature changes from about 20 Kelvin at the liquid level to about 80 Kelvin on very top. So again, it's important if you're trying to vent hydrogen out, so you need to know it with what energy it's leaving from the system. And the additional study we did here is to modify venting tube. So instead of just venting para-hydrogen, so we're assuming we put catalyst on this tube and it's converted, at least partially, into orthohydrogen when it's vented. And what it does, it absorbs heat from the tank, since para-orthohydrogen conversion is associated with either release or consumption of the heat. So in this case, when hydrogen flows through this tube outside, so it also produces cooling effect due to this conversion on surrounding gas inside Ullage space, and you can see there was lower temperature in the Ullage formed when you basically activate that conversion, which showed that we can reduce losses, venting losses, by about 10 to 25% in these cases with reasonably high heat leak into the system. Right. So now we will again switch a little bit direction and look at the modeling of high-speed hydrogen flows. Right. So previously we talked about storing liquid hydrogen in the tank when both liquid and gas are essentially static. So there's very little flow. So basically you don't need momentum equation to predict evolution, right, of the system. So now we will look at a different scenario when we have high-speed flow through the pipe or like nozzle. And in this case, so you need to look at all governing equations. And I will show how we apply computational fluid dynamics in this case. And the scenario we're modeling is critical flow when pressure outside drops below a certain level, then flow rate through the pipe or any opening becomes insensitive to that ambient pressure. So you're reaching choked flow. So they call it critical or choked flow. Flow rate becomes insensitive to what you have outside if pressure is low enough. So it's important, again, for liquid hydrogen transfer systems, also for safety. So if you have some damage in the tank, so you want to be able to predict what will the flow rate of hydrogen may affect if there's fire outside. So you want to know what will the flow rate of hydrogen if there's very large pressure difference. Right. So in this case, we applied computational fluid dynamics for the system that was tested 6 years ago, something like that. They published some data where there was liquid hydrogen in the tank, so it passed through this tube into expansion chamber at much lower pressure. So here I'm using computational fluid dynamics, which runs models for turbulence. We need to account for multiphase flow, so it's done using volume of fluid analysis, and we're modeling phase change using already embedded in that CFD relaxation model, homogeneous relaxation model that has certain parameters, right, that they were validated previously for water flow, but they may not be applicable for hydrogen. So the goal of this study was to find the appropriate relaxation parameter here so we can match experimental data, and then we will, if that's possible, then probably we can use it for liquid hydrogen systems, at least in configurations and conditions similar to what we study here. So this is an example of discretization. In CD, you need to create some kind of domain you're modeling. So I just looked at quarter part of the system, that end of that tube into expansion chamber. So you need to define boundary conditions, inlet on that side, some symmetry planes, pressure outlet in that chamber, and no slip wall along that tube. This is a numerical mesh. So again, you need to build dense mesh where significant fast processes are happening. That's at the exit of the tube, right? Relatively dense mesh inside the tube. And you also need to do mesh verification studies when you vary density of the numerical discretization of or number of cells in the domain to see whether results converge to certain values. So here, metric of convergence was math flux, and basically it demonstrates here oscillatory convergence, but it approaches, so it starts from 35 here, going to 39, and going back to 37. So it's and converges to a certain value. So you can estimate numerical uncertainty there, right? There is specific procedure for that, and so we assume so the result for numerical uncertainty about 3% of this mass flow rate in this case, right? So then using that model, so we can change parameters in the phase transition submodel to match test results, right? The blue line here shows the experimental mass flow rate through the tube, and horizontal line is essentially relaxation time parameter in the phase change model, right? So if you increase that time, right, flow rate will increase. So it means liquid is maintained longer inside the tube. If phase change happens faster, then it will evaporate quicker, and if you have more vapor, flow rate will be smaller. So liquid is much denser. So then we found that at this value of relaxation time parameter, we get reasonable match with conditions. So we can recommend it at least for configuration close to what is shown here. So these graphs just illustrate inlet void fraction in the flow, basically amount of volume occupied by vapor. So you can see variation. So yeah, I guess these show not the volume fraction, they show pressure in the system. So we start with high pressure, pressure drops at the exit of the tube, right? It drops to minimum value. Then there is some recovery. So kind of small shock wave is formed here. So if we look at center line profile, you can see this pressure jump here. So that corresponds to shock wave. So initially you have expansion, then local increase of pressure. So I guess volume fraction is shown on this graph. So again, in this case, we start with liquid only. If we go along center line, then there is significant evaporation happening when pressure drops, and then again, some vapor will recondense and we'll have more liquid in the system, but still most of the volume occupied by vapor. So we studied also different inlet conditions. This is the difference shown here with some liquid and vapor mixture present at the inlet. So then in some situations, you don't see that shock wave, say pressure at the inlet is smaller than certain number. All right, so now I'll just show an example of this model applied to my more interesting case, convergent divergent model. Right, so we're using the relaxation time we found from calibration study. This is an evolution of flow rate inside this nozzle with decrease of pressure. So essentially, if pressure decreases, flow rate will increase. So pressure outside decreases, flow rate will increase, but then it will stabilize. So it will no longer change, even if we keep decreasing pressure outside. So it means we reached critical or choked flow in this case. So you can see maximum velocity is attained at the throat. There's low pressure here, right? Some liquid, so liquid is in blue, it starts evaporating at the throat, right? So you're getting mixture at the outlet and this temperature evolution. So basically, if you continue decreasing pressure, even if you go to vacuum state, flow rate will still stay the same. So it's known as choked flow condition. That's very important when you try to analyze certain accidents. If you have small damage crack in the tank, it's escape of hydrogen. So you want to know the flow rate of hydrogen at the given dimensions, pressure difference. So I believe this model can capture this behavior. Right. So going to more like the complex flow, now we'll look at reactive flow, where para to orthohydrogen conversion occurs. So motivation for that was again catalyzing the venting tube in the tank. So if you put catalyst here, if you move para-hydrogen through the tube, in the presence of catalyst, it will be converted to orthohydrogen, and that conversion is associated with heat absorption. So this tube acts as a heat sink. So essentially, you're intercepting some of the heat leak coming into the system, and you're cooling down the Woolwich space. So how we plan to do that? So we use a device known as vortex tube. And so it's an interesting device from fluid mechanics perspective. If you inject high pressure gas and form vortex inside this tube, and it will have two openings, one at the core close to the inlet, right? One will be peripheral flow. Even with compressed air, you will observe that air escaping from this core outlet will have lower temperature. So this is actually used in some practical applications to produce cooling effect if you have compressed air stored somewhere. But we wanted to apply it for hydrogen cooling. So we thought if we put catalyst on the surface of this tube, since temperature of this flow in this direction will be higher, so it will trigger more effective conversion of hydrogen from para to ortho form and produce cooling effect, so we can again absorb more heat from the Woolwich. So we conducted experiments with this system. So this vortex tube, and shown here, this like liquid hydrogen system. Then this liquid hydrogen is heated and can pass it through that vortex tube, measure para to ortho hydrogen concentrations using Raman cells. Right, we send laser signal. It excites hydrogen based on response. You can identify what's the fraction of ortho hydrogen in the system. We put catalyst inside the tube. So this is just cross-section of the tube. You can see internal surface. So we distributed ruthenium catalyst inside it. And then we also tested systems without catalyst, just to make sure we see more conversion in one case, less conversion in the other case. Right. So we collected experimental data, but if you want to apply it to model, say, effects in different systems, so you need to know what's the conversion rate, right, in this geometry with this catalyst. So we use CFD results, CFD simulations, again, calibrated our CFD model to match ortho hydrogen concentration at the outlet to get effective conversion rate of para to ortho hydrogen in the system. So how we modeled it, so this is just cross-sections of the spaces occupied by fluid, right? So we have high pressure tank on top, then we have nozzles, which are essentially those channels. They come into the tube. So red areas here show velocity. Maximum velocity was 500 meters per second. So in some cases we exceeded speed of sound, so you can create supersonic flow here. Then you form vortex, and then we model it, the region where conversion occurs as thin layers near the tube walls. That's where a catalyst was deployed, right? So then a fluid particle is inside the zone, then conversion happens with that rate. So again, I changed just parameter in this reaction equation and found at which value we're getting agreement with experimental data. So again, we measured ortho concentration of the outlet. We found that this value, so we get best agreement. So again, we can recommend this equation to predict what will happen in systems similar to this one. So now I will quickly show maybe a few simulations for different liquid hydrogen systems. So this illustrates sloshing in the tank. So again, when the system is steady, you can see temperature distribution forming. Then you start moving tank horizontally. It's called slosh, and then liquid will start moving. So this liquid hydrogen in the bottom, all space on top. Right? The temperature becomes more uniform since you're mixing more efficiently. So again, we can trace pressure and temperature outside. This is important for transporting liquid hydrogen, since you need to know how pressure and temperature will evolve in order to select tanks or know when to vent them or how much hydrogen you will lose due to venting. Right? This is another important event when liquid hydrogen is added to the system. So here it's done through the tube on top, right? So you pour liquid hydrogen, so it occupies part of the tank, right? Again, there's some temperature stratification occurring both due to compression of the fluid, heat loop. Again, with CFD, and with calibrated CFD, you can predict what will happen, what temperature and pressure you will expect. And that's important practical applications. Right. So now let's look at another phenomenon associated with hydrogen flows. So when you transfer hydrogen through the pipe, so often there are significant heat leaks. So liquid hydrogen will start boiling. So boiling is a complex mechanism, and there are different regimes that can be present in the pipe. And this figure just illustrates what happens if you start with liquid and you're adding heat. Pipe is sufficiently long, so initially you will see small bubbles forming. When you reach temperature of boiling temperature here, then these bubbles will grow in size, merge, so you have more and more vapor phase. Then you will see on the annual flow, liquid is present close to the wall, maybe with some droplets inside, then this liquid will evaporate. This is called dry out event. The temperature of the wall increases significantly. Then, since there is less heat transfer, if you have gaseous flow, these droplets will disappear at some point if you keep adding heat into the system. So it's quite complex transition here. But what's really important for reliable liquid hydrogen transfer is to understand whether this can lead to some instabilities in the system. And there are many types of instabilities associated with pipe flow when you have flow boiling. So I listed them here. So sometimes they involve additional components such as pump, surge tank that have certain dynamic characteristics that will be coupled with dynamics of the boiling flow in the pipe. Right? You can excite acoustic modes. There we'll talk more about acoustics a bit later. But here I want to present analysis of density wave oscillations. So this is a phenomenon when you have just long pipe, you're adding heat. And at some point, even if you keep external parameters the same, so heat added, pressure difference between inlet and outlet, your boiling boundary will start moving, oscillating. So sometimes you have mainly liquid in the system with two-phase close to the outlet. Then this boiling boundary moves to the left. You'll have more two-phase. Again, this happens even if you maintain same boundary conditions, same heat added, same pressure difference. That's why it's called density wave oscillation. So it's self-excited oscillations. So how can we model that in simplified manner? So we can consider one-dimensional flow, and apply homogeneous two-phase flow model, neglect subcooled boiling, right? Again, assign given heat and pressure difference. Then we can formulate governing equations that involve just continuity, energy, momentum equation plus equation of state. Right? These are written in one-dimensional case, so Z is coordinate along the pipe, T is time. So this is continuity equation. So G is mass flux, density times velocity. This is energy equation. We're ignoring some minor terms here. So Q is heat flux into the system. This is momentum equation. Then you have evolution of momentum in the system, pressure gradient plus frictional losses and minor losses at the exit and entry. right? So these equations can be integrated in time. So you need to use an advanced solver for that, since these are nonlinear partial differential equations. So you need to use implicit staggered upwind numerical schemes to get rid of numerical instabilities and predict just physical instabilities. And what happens using this model, you can basically figure out when instability occurs. So here I considered system with given parameters. The only variable is supplied heat flux, right? And I analyzed two cases close to stability boundary in the stable and unstable mode. So if heat is smaller than that critical value, then upon initial disturbance, system will end up in stable conditions. So all fluctuations will disappear. You will have pressure distribution. You can see here that's distribution along the pipe. However, if you slightly increase this heat addition, then system may become unstable and enter the limit cycle oscillation. So all properties will oscillate in time. These are basically pressure difference, pressure drop, excluding the minor losses. These are mass fluxes at the inlet and outlet, this outlet void fraction. So system becomes unstable, and it's then difficult to use it for liquid hydrogen transfer and then complicate things. So basically we want to predict when this happens, maybe modify the system to avoid those instabilities, or understand if they will be present for a certain period of time. Maybe the system gets cooled down, right? And heat flux will decrease, these instabilities may disappear. Again, it's important for practical applications. Right? And using this model, we can also consider some systems, change parameters, figure out what will be stable at operational conditions and unstable. So typically, density wave oscillation, so we use non-dimensional parameters. One is called subcool number, so it characterizes subcooling of the liquid. Second, it's phase change number, so it's basically heat flux delivered to the system divided by mass flow rate, normalized also using some fluid properties. So if you have relatively low heat flux on the left side, system is stable, right? If you exceed heat flux across the stability boundary, oscillations will appear. And we studied how different effects can affect that stability boundary. So for example, if you consider vertical and horizontal tube at the same other parameters, so vertical tube will be more stable. So you will need more heat, right, to excite the system, since gravity will stabilize the flow. So basically, again, for practical applications, you can put parameters of your system and figure out whether it will be prone to instabilities or not. Right. So now I will switch to thermoacoustic instabilities. So these are different from multiphase flow instabilities I described before, since they are associated with just gaseous hydrogen without mean flow. So why are we interested in that? So it's very important for cryogen storage. So when you have tube penetrating tank, you may need to put sensor here, you might use it as venting or supply tube. Then you have significant temperature gradient along the tube. And at some conditions, that gradient can cause acoustic mode to become unstable. Then you will excite oscillations. There will be sound waves going back and forth here. Again, even if you don't impose those oscillations intentionally, you just have large temperature gradient, the acoustic mode will be unstable. So that's why these are called thermoacoustic phenomena. So these phenomena originally, they were studied more with application to high temperature systems. So for example, rocket motors, if you build new rocket motor, it will likely to be unstable, blow up eventually. And most instabilities come from excitation of that acoustic resonance. So when you're releasing a lot of heat, part of that heat is coupled with pressure oscillations. So you may add heat in phase with pressure oscillation that will amplify acoustic mode. Eventually, loads will become too much for the combustion chamber and will destroy it. Right? So similar phenomena happen in cryogenic systems, but at low temperatures. So you need essentially very high temperature difference. And this process can be also inverted. You can pump heat from cold space using sound waves. So this is implemented in pulse tube cryocoolers. When you have porous matrix and you impose sound waves, maybe from acoustic driver, and you arrange system appropriately, you can produce heat transfer from cold space to hot space, reducing acoustic waves. This is commonly used in cryocoolers. So again, this is the name of cryocoolers that operate on acoustic principles. Right, so the reason for those acoustic instabilities can be explained with Rayleigh criterion. And so if you have acoustic wave, you add heat to the fluid particle when it's compressed and extract heat when it's expanded, then energy is transformed from thermal form to acoustic or mechanical form. So equations can be written to verify that, and that's what's happening inside those tubes that penetrate cryogenic tanks. So you have very large temperature gradient, and if acoustic phase is appropriate, so the acoustic particle becomes compressed on left side at the warm space, so it will take heat from the wall, release it when it moves to that side. Right. So again, our interest in this phenomenon is primarily for liquid hydrogen systems. So this is liquid hydrogen tank. As you can see, there could be 20 tubes penetrating tanks. So they can be used for, again, supply, extraction of hydrogen, venting, sensors. So there are a lot of opportunities for these instabilities to develop. So even if some of these tubes get those acoustic oscillation excited, then you might get significant additional heat leak into the system, since basically acoustic flow potentially leads to convective heat transfer. And users of these tanks, companies we're working on, often report that they're seeing unusually high heat leak into the tank, large boil-off rates, much larger than makers of this tank predict or specify. Again, this happens in some operational regimes. They don't know why, but we can suggest that it may be happening due to thermoacoustic instabilities known as Taconis oscillations. And it's difficult to pick up experimentally whether these oscillations occur, since usually they use static pressure gauges that may not respond to high frequency acoustic oscillations. So they don't really know. You cannot hear them since they're happening inside the tubes. And pressure sensors, conventional static pressure sensors, will not show anything. But there could be high frequency oscillations happening. Right, so how to analyze this process? So we can apply one-dimensional acoustic theory in ducts with losses. There are standard equations. Basically, if you assume that you have harmonic oscillations at small amplitudes, so Navier-Stokes equation can be brought to these linearized oscillating forms. You can get rid of time derivative, right, if you use harmonic oscillations. But in the presence of temperature gradient, you will have additional term that can lead to either excitation or dampening of oscillations. It depends on temperature gradient. So if sufficiently high, you have the appropriate place, then system will become unstable. So this is an example of calculation what happens along the tube, starting from warm end, closed end, to the open end in cryogenic tank. This is how acoustic pressure amplitude mode will look like. So pressure amplitude is highest at the closed end, close to zero at the open end. Acoustic velocity behaves opposite way, so it must be zero at the closed end, maximum at the open end. So acoustic power will be generated in the transition zone where there is significant temperature gradient and it will flow in both directions. So basically you have dissipation outside that zone and power production in the zone, right? So previous studies in this area were related to helium, but we wanted to verify for hydrogen whether this theory is still applicable. So we constructed experimental system in our lab, right, that's shown here. That's what's inside cryostat. So this is long tube, it's coiled in this case for compactness. So we can control temperature on the cold end. So we know temperature at the outside. So we know geometry of the system. We can change mean pressure and fluid inside it. So we characterized stability boundary, right? This is an example of experimental runs. If you gradually reduce cold temperature, so system at some point will become unstable. You will see oscillation. We put acoustic sensor, in this case, dynamic pressure transducer, that could pick up those oscillations. So we saw that magnitude of oscillation increases, right, if you increase temperature gradient. So we can verify theory compared with experimental data for both helium hydrogen systems. So we found hydrogen systems are more prone to those oscillations, since viscosity of hydrogen is several times smaller than that of helium. So it's, I guess, this liquid hydrogen storage system may be more susceptible to these instabilities. That's why users of liquid hydrogen tend to see sometimes high boil-off rates due to additional heat leak due to Taconis oscillations. So again, we did parametric studies. So there is optimal radius of the tube, optimal lengths, optimal ratio between warm and cold zone. So you can use these results to basically design the system that will counteract those instabilities, will be less prone to those instabilities. So you can select radius either smaller, larger, to avoid those. So there's some optimal range when these instabilities can be excited at lower temperature gradient. So also if you put wider section at the warm end, and that's what often done, practical systems say you have bigger sensor here, system will be more susceptible to oscillation. So if you want to suppress, then you want to avoid wider sections. Right? You can also assess heat leak, this analytical solution in case of laminar flow. This is an equation you can use, just calculate heat leak if you know acoustic pressure amplitudes, geometry of the system, fluid properties. So up to 100 watts can be observed in practical systems. So you can, experimentally it was shown that boil-off rates can increase like 3 orders of magnitude in comparison when you have just ordinary heat conduction. So if you have those instabilities, they can be very large heat leaks into cryogenic systems. Again, it's of convective nature, have oscillating flow, just transfers heat from warm section to the cold if you have fluid oscillating between them. All right, so you can mitigate some of this phenomenon using oral sensors, so you can try to suppress oscillations, so add resonators in specific points and to absorb those oscillations. But this study also made us think whether hydrogen can be used as more efficient fluid in cryocoolers than helium, since it's more prone to thermoacoustic phenomena, it has lower viscosity. What if we replace helium in cryocoolers with hydrogen, at least in some temperature range? Those devices might be more efficient. Right? Since that's a big problem with cryocoolers, they have very low efficiency, they operate at very low temperatures. And previous experiments in the 70s, where somebody tried to put hydrogen, they actually saw some improvement, but due to economic reasons, less understanding about hydrogen safety, this were not implemented in practice. But currently, we are working both experimentally and theoretically investigating this phenomenon, and specifically we are looking at how hydrogen liquefaction can be enhanced, since you need to also convert, again, orthohydrogen into para-hydrogen during liquefaction. Why not use this porous matrix, right, to extract both heat, if you use it as cryocooler, and catalyze it, right, to make this conversion. So you don't need additional catalytic bed, so you can make the system more compact, there will be less losses. So if you impose mean hydrogen flow through cryocooler with porous matrix, you can pump heat out of existing hydrogen, and you can also convert it simultaneously into para-hydrogen flow. Right? So that's what we can explore in modeling. So we published some papers. We actually saw that the extended wave device, so performance of hydrogen system with second law efficiency can be increased by about 30% in optimal regime in comparison with helium system. And again, all essentially current cryocoolers, they use helium. But if you replace it with hydrogen, optimized system for hydrogen, you can reach much higher efficiency. So that's what we're currently working on. So we're trying to develop experimental systems to validate that. So just in conclusions, right? So we developed reduced order models, CFD simulations for cryogenic hydrogen. So in these simulations, we use real properties of hydrogen. Validation was performed for some of the flows and conditions. So these validated models can be used to improve design liquid hydrogen systems, but there are a lot of other opportunities for modeling in this area, right? So you can also look at different devices that operate on liquid hydrogen, study multiphase flow instabilities and so on. And I have just one slide on this book. Probably Poland already told you about that. Right. Yeah, thank you very much. Any questions?
Thank you very much for many interesting examples. In your modeling of the liquid vapor transition, you seem to take the energy and the mass balance along. Is that because the entropy balance doesn't play a role, or have you looked into the excess interface properties?
So I guess to model evolution, so you don't need entropy balance. I don't think so.
You don't think so?
Yeah.
Well, but I think maybe you should involve more people in that discussion. I think it will change the heat flux.
Like entropy is usually used like to optimize the system. If you want to look at the sources where entropy is generated, then you apply exogenous entropy analysis to figure out where is opportunity for improving system performance.
But the model may be very well conducting, and then there are no jumps across the interface temperature. Did you see any jumps experimentally?
Yeah, we don't have yet enough resolution to see temperature profile close to the boundary.
Mm-hmm.
So we only measure bulk temperature, both liquid and gas. So we don't know. So in modeling heat transfer towards or mass transfer across the boundary.
Mm-hmm.
These are complicated processes, and right now we're just using some empirical correlations. So we have experimental data from different studies, and we're just adjusting parameters in those mass or heat transfer rates to match experimental data. We're just using that for prediction, but we don't really understand the physics of that evaporation. So we are not even attempting at this point to figure out why mass transfer rate is this way. So just try to describe it rather than understand what drives that.
Yeah, just maybe it's a related question, but when you discussed the flows in these large containers, you didn't say much about the boundary conditions, but at the same time, you have a wall where there may be large heat leaks. I saw numbers of 10 kilowatts per square meters, which could imply that there might be a kind of Leidenfrost effect at the boundaries, and that therefore you might go from non-slip to slip boundary conditions. Is that an issue at all?
Yes. So again, we're not with large tanks. We're not trying to model flow inside this tank. We're just assuming certain heat into the system.
So, but even for the sloshing, it doesn't make a difference?
No. Sloshing is different. For sloshing, I'm just assuming certain either temperature or heat flux at the boundary. So I'm not yet trying to resolve, say, temperature distribution in the tank wall, which is also important, or some microscopic features in the flow.
But I guess you would like to have these systems as insulated as possible then.
Yes, of course.
So the leak is usually preferably very small.
Yeah. But in some cases, like during chill down process, for example, will be inevitably large.
Yeah, very nice, Konstantin. I'm wondering about this, cooling by acoustic, instabilities. That's a, pretty cool way to cool stuff. But Do you have some thought about the efficiency there? Because you said you needed large temperature gradients. What type of efficiency compared to regular cooling do you get?
So there are pulse tube cryocoolers. So best ones might be close to 15% Carnot efficiency.
Yeah.
15, yeah, of Carnot efficiency. So actual efficiency, very low.
Yeah.
But because of very low temperature. But what we showed, like hydrogen systems were more efficient than helium. And helium pulse tubes are commonly used. So these cryocoolers operating on sound are already used. Just they're using it with helium, but we want to replace it with hydrogen. And also currently they use acoustic drivers, which are linear motors, very expensive, require maintenance. It's large mass, going many cycles per second. We want also replace it with thermoacoustic engine. So outside the tank, if we have some heat source, you can use vented hydrogen, right, burn it to drive thermoacoustic engine that will produce acoustic power, deliver it to a cryocooler that will extract heat from the tank. So this way, either if you have extra power outside the tank, you can pump heat out without any moving parts. That's another advantage. There are only sound waves. There is no mechanical parts. Then it means there's no maintenance needed, essentially. System is very robust. They actually designed those for submarines and spacecraft. So if you have system that goes outside and solar system, they actually use radioactive plutonium to create heat source. Then you generate acoustic waves. Then electroacoustic transducer, in this case, there is mechanical part, but it converts it into electricity to power sensors. Because if you're far from the sun, there is not enough solar energy anymore to produce an electricity for sensors. So they're designing systems right now that operate on thermoacoustic principle. But it's to produce electricity from heat source.
Yeah.
And they believe the systems will be more robust than any other systems.
What about safety issues about using hydrogen versus helium in the cryocoolers? Is that a concern for people?
I guess we're comfortable.
Yeah,
so our goal is to educate others so they can do it safely.
Yes, if you.
That's why we're providing also training for other people from industry.
Yeah.
Sometimes, if you want to come visit us for a few weeks, learn about hydrogen, welcome. Sometimes, people come from other universities just to learn and start liquid hydrogen research in their labs. You want to do that, We're inviting you. Send us few people. So they will assemble system, liquid hydrogen system, right? Pass hydrogen through, so they should learn enough to start research here. So there is significant initial barrier, but once you learn it comes natural.
Yeah, I've heard, I think it's maybe Jacob Leishman who said it, that liquid hydrogen wets all surfaces. I mean,
there is, I don't know about, what's contact angle. Again, it's microscopic feature. I'm not even considering that in my models yet. We know surface tension, but whether it wets surface, solid surface, need to know contact angle.
Because I would guess that maybe would increase the heat ingress if the liquid is wetting the ullage.
But that's why I very like empirical correlations, which validate our model. It means it's not applicable to all systems, so it's just applicable to a range of conditions that validate it. That's, I guess, another opportunity to study that. We tested some liquid nitrogen system. Now we also built visualization system. So we're trying to look at the flow, multiphase flow through the glass walls. So we have cryogenic chamber, liquid cryogen flow, transparent section. But so far we studied only liquid nitrogen. But we saw a lot of things. Even if you have liquid flow and gas on top, there are a lot of small droplets and bouncing on the surface. So quite different from water flow. Water flow is more stratified, but with cryogens, yeah, there's latent frost effect, other things. Different, yeah, surface tension, contact angle. That's why, yeah, you need more studies to understand what's going on. Hopefully, yeah, maybe this year or next year we'll start looking at liquid hydrogen flow. So we'll have video, maybe photograph. Our close through the pipe with heat addition. So our oils better, best surfaces or not.
Okay. Any more questions? No, let's thank the speaker one more time.
If some of you are interested in discussing